Everybody can hear me, is that right? So those who are online should speak out if you have any questions, because obviously I cannot do all of this and then watch the chat and questions there. So I would like to hear your voice if you wanna ask a question while I'm presenting something or any other comments you may have. I hope that you guys can hear what I'm saying. Can you hear me? So I'm asking a question, if somebody can tell me, those who are online.
Yes, ma'am, we can hear you.
Thank you so much.
Yes, ma'am.
Thank you. Okay, so today we are starting with the 4 forces of nature. And when you want to look at the material in this class, you will come here. And then from there, you will see this presentation here. And you can do it like this. So, as it says here, we all at least have been told that we know that there are 4 forces in nature. And these forces are the ones that we have been able to feel or to measure, okay? Which one of these, or which 2 maybe of these, were the ones that we were able in human history to feel first and identify as something very specific? Number 1 and
3.
And 3, exactly. Number 1, gravity. Obviously, we all feel that we are heavy, and then we somehow, whenever we have to be attached directly to the first, object we touch with our feet, and we are attracted, to the ground in some ways. So that was something that people understood first. And then, of course, without knowing exactly what was happening, that was the first kind of force that we understood on our muscles. And the second one was electromagnetism. I think I did something here. One second. Okay, I don't think I can do it. It sounds very, anyway. The second one, how did we find out? How did people find out that there was this kind of other force? Well, magnets came later, all right? The first thing, people were making jewelry, if you know, years ago. Even since part of the human history is that we were making different things for rituals, for decorations and so forth. And when they were taking these glass-like little pea balls and then were trying to shine them, obviously to place them around their necks, in their hands, whatever, crowns, if they had shorts or whatever other things, they found that they were attracting small things. So they understood that there was something there that was temporary, obviously. It was not permanent. And that's how they started thinking eventually about those things. And since then, we were able to understand more about gravity, of course, and electromagnetism, but also we've learned about the other 2 forces, which are nuclear forces, all right? And let's start about gravity, first of all. Gravity is a force that you see in large scale at the macro level. It's one of the forces that becomes extremely prominent when you are at large scales and the large masses. And so tell me an example that we know of.
It's 3 o'clock.
That's my computer, don't worry. This is just for me. So there are in universe, obviously, all right, our solar system. I mean, gravity is what, it's a big force that is moving, it's moving the galaxies, is moving the stars, the planets around the stars, the satellites around the planets and so forth. And of course, a major a major example of where this force is amazingly large is in black holes. And if you remember, people received, a group of people received the Nobel Prize for, first of all, using Einstein's theory of relativity to theoretically predict the presence of black holes. And then, of course, now we have observed them. And how do you observe a black hole? By seeing nothing. And why is it that we don't see anything? In black hole, what is it? It's like a point of singularity in terms of density, mass density. So it's where mass goes to infinity, especially the density. So all of the mass comes into one point, if that is possible. And then what happens when you have that kind of singularity? Whatever comes into close proximity gets attracted. All right, so what is it? All of the, and what and where do you know, where do you think those black holes are situated in the universe? At the center of mass. At the center of our galaxy, we have a black hole. At the center of any other galaxy are black holes. All right, so in fact, if you see black holes, they are not here, but if you see a black hole, and let me see if I can make this smaller and then draw something. Okay. Well, I will not try to do that, but if you see, this does not behave very well, so don't worry. If you see a black hole is like around it, there is a cloud with a structure of mass, like lots of stars that they go like in this helix down to the center. So at some point, every galaxy is gonna be absorbed by a black hole. What happens on the other side of the black hole, do you know? Is the black hole like a sphere? Is it like, what is it? I mean, does it have one face and another face? What do you think is a black hole? What happens? I mean, what happens to all of this that goes to the center? Do you think it stays there?
Parallel universe.
It's going out from the other side of the black hole like one line of energy. So the black hole absorbs mass on one end and then shoots out energy like a laser. I mean, like billions and billions and trillions of lasers together. So this is what happens. So what is it like a black hole? Is first of all using gravity to get mass to go there. And then what happens when mass goes there and collapses? All of the nuclear forces take over. And then all of this mass is turned into energy. So a black hole is like a transformer from mass to energy. So if all of the black holes were to transform all of the mass in the universe into energy, then what would happen? There is a new theory that says, then there is this other phenomenon that turns energy into mass, which we call, because we don't understand it, the Big Bang. All right, the moment that out of a space full of energy, there was the first atom, the first particle rather, before you go to atom, the first smallest particle that was created, and then there was like an avalanche. And then there was this huge moment when the universe was generated and all of the energy was transformed into mass. There is a theory I was reading very recently that people believe that this takes place continuously. I don't know. I'm not the one to confirm, but it does make sense in that setting, all right, of information that we have generated. So in any case, gravity at a large scale, first gravity to attract the mass, then of course, the nuclear forces, of course, it's the electromagnetic forces that keep the atoms together, and then the nuclear forces that collapse them. And then all of this becomes energy. So that's the process of these forces that we have seen. Now, people believe these two are planets that because of gravity and because they have, the interesting thing is like, if you have a big mass and a small mass, the small mass, if it were to come with a speed, with a velocity, not like it would come, like moving towards the big mass, is going to start going on this kind of a helix, all right? Closer and closer until it collapses. But if you have two masses that are almost equivalent, what happens? They go like that. They turn one around the other. And eventually the larger one is going to win. But they will do this for a long time. And why do we see this? Because at the time when they do that, they irradiate, they pulse, all right, energy, and we see those pulses in the RF field. So the amazing thing in all of this is we have defined those forces, but they're all connected. They're not like, there is this very smooth transition from the impact of one to another. And in a repetition that goes forever, assuming that, of course, that we never lose any energy or the sum of the two is always the same. Now, there are a lot of things that we don't know yet. A lot of people are talking about another force, but we are not sure exactly what it is. Now, this, we talked about the nuclear forces. You will see that the electromagnetic force, obviously. The first thing about the electromagnetic field, all right, the electromagnetic field, a major demonstration of the electromagnetic field is on our planet. Why do you think, what is the one single reason, in addition, of course, to the conditions where we are, how far we are from the sun, and then the temperature and all of this? Assuming that all of those, we take them for granted, they are there. What is then the one single reason that we have been able to see life on Earth? The magnetic field. And why is the magnetic field important? What does the magnetic field do? Yes, what does that mean? That if there is a particle that comes like this, then it's going to go around the magnetic field and it's going to go and pass us. So there are a lot of particles, like from all of these particles that they come our way, only a very small percentage is going through the magnetic field and reaches us, and then through the atmosphere and then comes to us. And that's very important. And now our bodies have been developed so we sustain that kind of density. If for some reason the magnetic field were to go away, the atmosphere then would go away, and then what? And with that, the rest of us. Immediately, in a very short period of time, considering the events. Now, why do we have a magnetic field? Iron, because of the iron core. So what happens, we will see that, all right? So what happens when there is iron and that is moving? It's like you have charges that are moving. What happens when you have moving charges? You have
Creates a magnetic
current.
field.
A current, exactly. What happens when you have a current? You have a magnetic field. All right. So the magnetic field, this is the process that really has been the magnetic field has been created, which means that if at some point in the Earth's life, that thank God goes billions of years after us, and if we have survived ourselves until then, we will be someplace else, my guess is. But when Earth dies, because the core is going to all lose that energy, and the magnetic field may go away, all right, because it's not going to spin, it's going to solidify. Then other things will happen by then, my guess is. But then, you know, life, then the planet is not going to be any different from other planets who are at the same distance from the sun. They had the potential to develop the same kind of conditions, but they don't have that magnetic field, or it's very weak. So very interesting things to see, the things that we see in our day life, all right, that in fact are the things that we'll try to study in this class. Now, you may wonder, here it shows, in fact, how the magnetic field, in fact, it shows here what happens, all of the particles that that the sun is shooting away, and especially you have more of those during these solar explosions that you see on the surface. These are nuclear kind of phenomena. And then you have all of these particles that are coming, but you know, they're going away because of that. There is, what happens to our solar system? We have one on our planet that saves us, a magnetic field. Do you think our solar system has a magnetic field? Yes, and it's called the heliosphere. And protect us then, that is one shield, if you like, the heliosphere, and then our magnetic field is the second one. All right, so for the same reasons have all been developed, these magnetic fields. All right, now you may wonder, okay, here in this class, we are gonna learn electric and magnetic fields. So why are we starting with forces? What is the difference between a force and a field? Have you thought about that? A little louder so that everybody can hear you. So the force is something we feel, all right? Something we have been able to feel because of our mass and been able to identify and measure. The field is not of the same thing. The field is a construct, is a mathematical construct that we have developed to be able to understand the result of those forces, all right? The electromagnetic forces are responsible for a lot of things that we see. For example, if you read Feynman's, one of the early lectures that he got the Nobel Prize in physics, if you read some of his early lectures, he used a very simple example. He said, why is it that a human who is made out of billions and billions and trillions of molecules, and every molecule is made out of billions of atoms. Well, not exactly, depends. Cells, I should say. A cell is made out of billions of atoms. Why? And all of this, there is space. Do you know how much space there exists between the nucleus and the electrons? If somebody were to condense us, forget about water and everything that we have in our body. If somebody were to condense us and say, we'll take everything you have and we are going to eliminate the space, do you know how much little space we are going to, all of our thing will be, you will not be able to see it. The distances between the atom and the electrons and inside the atom between the particles are huge. Why are those distances there? If they are huge, practically I could sit on this chair and go through, all right? Because the chair has the same. and all of my atoms could go through the chair. Why do they not go through the chair? Because of the electric forces. That's what keeps our structure together. We are one. We are not like a collection of atoms that all go and disappear on the ground. All right, we are who we are because of electric forces. And why are we sitting on the chair? Because of gravity. All right, that's the difference between the forces you see. You don't see the electric forces because they become important when you are at small distances. Gravity is more important at large distances. At small distances, gravity is not important. Yes. When you sit on a chair, you sit because your gravity takes you down. So you sit there. If you did not have electric forces, if somehow the forces were not strong enough, your molecules will go and atoms will go through the chair.
So the electromagnetic force when you're sitting down essentially bounces out.
Yes, exactly. Yeah, exactly. Or at least it holds. I should say it's not. It's quite. I mean, in general terms, it's true. The way it's not accurate the way we say it, but it's good enough for us to understand it. Okay. Just want to make sure. Now, what is the field, and why do we introduce fields? So I want to make sure. I will go to the next one now. Let me see. Okay. Now, if you want to go and learn more, I'll go to the next. Let's go to, I am back here. And then you see that I have a second document which talks about forces and fields. It's about the same, but in this one, you have this formula that shows you, and why is it that you guys, is it okay? Maybe I need to find out how to send this to your monitors there, but it's okay. I think everybody can see that. So you see, this is a known Newton's law for gravity. What is interesting in this, that the force, let me in fact, can I make it? Yes. Look at this. The force, which is gravity, is in this particular case, all right, considering where is the R1, 2 for this case, with a hat. Whenever you see something with a hat, that's a unit vector. We'll talk about that next week. These two masses, they feel this attractive force, which is gravity, obviously. And the gravity, this force, depends on the two masses. So now what happens with human beings? We want to measure this force. That's how we started understanding things, all right? We cannot conceptualize things because of our senses, because of the way we are made. We cannot conceptualize things without having an experience, all right? Our brain does not learn concepts without having an experience. You need to remember that. And that's why at some point, if I have time, I'll talk to you about what we call the embodied intelligence on how the brain learns. Extremely important. We learn from sensory stimulations, and we learn from socializing these experiences. And then that's how the brain goes to the higher level and creates concepts. But you cannot go and develop a concept without having some sort of experience. Very few people have been able to do that, and that it builds eventually, like the relativity theory that Einstein did. Of course, we did not have, I mean, we had some indications from measurements, to tell you the truth. Nobody can develop a concept from nothing. So in any case, let's assume that we want to study gravity, and I have myself, that I have a mass, and then there is another observer who is like a basketball player, who is like 7 something. And then it's more like the weight is mine plus 150 pounds. And we go now and somehow we try to feel, that's how we measure it, all right? First, to feel that force and then try to write it down to express it. Okay. My observations and this other person's observations will be impacted by our physique, which is mass in this case. All right, I will feel a force which is less than the force this other person feels. So if the two of us sit on a soft ground where you can leave imprints, this person's feet will go further in, all right, if it was a soft material than mine, because this person is going to have a higher force. What does that mean? That this person and I cannot have a discussion about the force. We experience different things, and we observers then pollute our measurements because of our presence. So then what did scientists think? Fine, what if I remove my mass? What if I take this out so I'm an observer and my mass does not impact the force? And what did that do? It moved from the force to something different, all right, which is just the same normalized by my mass, the mass of the observer. And what is that we created? That is a gravitational field. So the gravitational field is an expression of the gravitational force, but we have eliminated the effect of the observer. So if I am a person here, that's my mass, and this one, for example, is Earth with Earth's mass, then the force that I feel, if I divide it by my mass, then mine and yours, if the two of us, who are different people, all right, are at the same distance from Earth, then we calculate the same thing. Did you see that? Because our mass is not here. The only thing is here is just our place. And if the two have the same place, so if I go here and you go there, but the same distance, then what we will measure here is going to be independent of us as observers. That is a field. That is a mathematical construct that we developed to be able then, as a community, to identify the same entities, quantities, and then speak about these quantities and eventually communicate our observations and experiences, and eventually do what? Then think at a higher level, conceptually speaking, about what it is that we are observing. That's why fields are in place, all right? So that's why, and sometimes you say, well, I don't know what a field is, I don't see it. Of course you're not gonna see it. You're not gonna see a mathematical construct, okay? You're not gonna feel it. It's like you tell me, I don't see, in my real life when I go home, I don't see a vector. Of course you're not gonna see a vector in your car, all right? It's a mathematical thing. That's what a field is. You need to remember that. And the fact that you don't see a field is not something you should bother you. You should be looking for things that your senses can measure and observe, or you can experience. And that is going to be the most fundamental. And then you take it for granted that the field is the construct that we are going to use to be able to understand it, to understand the force we feel or the other experience. Coulomb's law, we will see that also again, you have seen it in physics. That's the force. The force we talked about that keeps together the nucleus and the electrons. That's the force. However, we are not gonna, if say I am a charge and I go to another charge, I mean, and then we measure the force because the force exists then, then in that case, depending on the charge that I have, I will measure a different force. And then so two different measurements that incorporate the characteristics of the observer, which is one of these two charges. Okay, this is the observer, this is like my charge, then it has to be removed. So what do? We remove Q1. What happens when we normalize with respect to Q1? We create an entity which we call the electric field. So don't tell anybody that I don't know what, and I cannot see. Why do we not feel the electric fields? Don't feel them because they are mathematical things. What you feel is the electric force. Unfortunately, we don't feel electric force ourselves. So this is some of the things that you have to keep in mind as we will move along the explanations that we will try to, first of all, understand what are the electric and magnetic fields from electric and magnetic forces. And at some point, when you feel comfortable about the idea, the concept of the field, then we're not going to go back to forces anymore. And we're going to work with fields only. It's like, for example, you say, well, the first thing that I'm learning is the alphabet. Okay, I mean, you know, there is a lot of learning about the alphabet. You have to learn and a few words. And then after that, you make sentences. When you move from learning the letters and then the words and to sentences, you never go back to the alphabet, all right? And say, well, I don't remember all the alphabet. What's the point? You don't need it anymore. So that's what is going to happen with us as we move forward. But there's going to be a time when we will have to feel comfortable about the fields. So what I would like to do next, now that we introduced why it is important to talk about forces and what the fields are, we're going to spend a week because I know that some of the math that we're going to use, you have had before, but maybe some years back, maybe some months back, but you know, it's good to have a review in the beginning. So everybody is on the same foundation as we start. And what are the things that we will have to learn when we start talking about forces and fields? Forces have a direction. They have and the same thing with the fields, because if you see in both cases, at least for gravity and for the electric field, we divide it by a scalar. So what we're going to do starting Monday, we are going to go through scalars, vectors, and tensors. We're going to introduce the concept, so we will use the same words. So when I use words, you understand what I mean, all right? And the same thing with each other. And then we are going to talk about vectors primarily, because scalars, we know what it is, all right? So temperature is a scalar. What is a scalar? A number that has no direction. Vector is a quantity that has a magnitude and has a direction. And tensors, we'll talk about that when we get there. So we'll talk about those. Then we are going to talk about coordinate systems, because obviously we live in a three-dimensional space. In reality, we live in a four-dimensional space. What's the fourth dimension? Time. And for some other problems, there are problems where you are multidimensional. Why? Because the phenomenon you try to understand and study has multiple variables. So every variable introduces one more dimension in that multi-variable space. So we're not going to go crazy. We're going to talk though about one-dimensional, two and three-dimensional, the coordinate systems we're going to use. And then Friday, we are going to go to vector calculus. And what I would like to do with you is to help you write math and understand physics. That's the important thing, because if you get stuck with math, then there is no way you're going to understand what it means physically. And it's very important to have to use, math is a language. It's not anything else. All right, it's a language we use to interact. It's an international language, as a matter of fact. We all use the same math around the world. And so usually we use it, if it's a language, we use the language to communicate concepts. All right. So we don't communicate math just for the sake of it, unless you're a mathematician, you solve a theorem. But for us who are engineers, we use math to communicate the physics, the problems we try to solve. And therefore we are going to spend one lecture, and then I will keep reminding you as we go forward, what are the specific things that will be important. Okay, so that is next week. What I would like to do right now is also to remind you that in every class, we are going to have an exercise, and the exercise is going to be either in the middle of the class if I want to look at the output and use that to stress topics, or it's going to be, as I said last time, at the end of the class in between two lectures, just to give you an opportunity to go and think briefly even for something, because that's how the brain works. All right, the brain puts everything, as I think I said, in the long-term, short-term memory, and the brain, because it does not have infinite capacity and works with a little bit much less energy than any other computer, what does it do? It keeps only what is important. And how does the brain think what is important? If a neuron sends a spike, and it comes from, like, say, if your eye sees something which is interesting and sends a spike to another neuron as information, if there is a sequence of those, that this information that I saw something is going to be recorded in the near-term memory. A lot of things we see are not recorded at all. And then what happens if I see the same thing again and is important, and I recall it from the long-term, the short-term memory that I saw it, and if I do this a few times, it's going to go in the long-term memory. So what is the goal in this class? To use these tricks and move the things that we are learning into the long-term memory. Because if you don't do that, what is going to happen? Every time you're going to have to do a review, it's going to be like you start from the beginning. You're going to ask yourself whether it was you that was reading this chapter like 3 weeks before then. So I would like to do the following. Now going back here. Let's see. Oh, let me see. Okay. What I will do is the following. You see that we are going to go into your tab hat, and I will show you what I have, and I will explain. This is the first quiz. Okay. For those of you who have tab hat, you may want to try to connect. So this particular one, just try to, I will assign it because otherwise you're not going to see it. But don't do anything. You know what? I think don't go into your own, just see what I'm doing here, because I'll tell you why for this one. Assign. You're going to be able to see it, but the moment you start solving it, you're going to have 5 minutes to do it. So don't try to go there. Just see what you're going to see this. And below it, I will do a review of this. In fact, I will not assign it yet. Unassign. Okay, I will do a review quiz example. Where is the review? Edit. I will do a review, a preview. Okay. All right, this is what you're gonna see. All right, so I have these two vectors, and I'll give you something, I'm sure you will need to remember it. So remember it before you go to do this. In fact, in this one, you're gonna get 60 points only for participation. All right, because we have not done the review. I give it this to you just to practice a little bit with Top Hat. 60 points for participation. In some cases, when you will need to do a little more, I will not put the time. Some other cases, I put the time here just so you experience it, all right? In some cases, I will give you time. From the time you start, you connect to it and you try to solve it, it's gonna take you 5 minutes individually. So I want you to experience that and let me know also how it feels. But most of the time I don't do that, to tell you the truth. So here I give you these two vectors and they have an angle theta in between. And when we do review on vectors, then we would need to know what happens if this, which is the length of the vector, A plus B. So if you take A and sum A and B and take that vector and the magnitude of this vector, we show it with two vertical lines. If that is less than the other one, then theta is gonna be one of these three. Will be either 90, less, or more, all right? So it's gonna ask you, you can move this, and then you can move whatever you think is the right answer, you can move it. So for example, if you think that if one is true, one is this, then A is true. If you think that, I'm not saying you should, but if you think that, then you will move, you will keep A there, and you're gonna move something else to the other locations, all right? But you can move those things, you can practice a little bit. Don't worry about what you're gonna do because you're gonna get 60 points for doing it. Just I want you to practice. So this one, for example, I could go next week and say, next Friday, I would like to give you a quiz like this, and I will give it to you, and I say you will have any time available that you find some free time. From the time you start working, it's gonna take you 5 minutes, but do it this between now and say Monday. I could have asked you, all right? And what that will do is, like, when I give you 5 minutes, it means that you should, if you had the material before, you should know in 5 minutes the answer to this problem. So it's a small thing, but what it's gonna do to you is gonna force you to think about it. And that is important. You don't have to spend 1 hour every day. I mean, I wish you could, in thinking about this, which in fact is gonna be great if you could, but even spending a short amount of time is gonna help you learn a lot better than if you don't. So the last thing I'm gonna say is the following. So we have a few more minutes. This late in my life, I decided to learn piano. And why did I do that? In fact, first of all, we had the piano from my daughter, who learned the piano when she was young. Now she's gone and married and everything. And we had the piano at home. So when we moved here, I brought somebody to tune it. And I thought, my God, we have a piano. And I don't know, my father was a musician, as a matter of fact, but somehow he tried to teach me and I hated it. So I never learned music. That's bad, all right, when your father tries to teach you. So after all of these years, especially with COVID, I was thinking, what is one way that I can get out, of the routine? So when the person who came to tune the piano, I asked him, a young Italian, I said, do you teach older women who know nothing about piano? He said, yeah, I do this. So I have to tell you the one thing, I have to play the piano at least 1 hour every day. You know why? Because I'm gonna forget it. I mean, if I don't play the song and I play all the songs, I play the new ones, and then even if it takes 45 seconds, to play one, short for me, if I don't do it for one day, I will forget it. And then of course, the piano is even more difficult because you have to learn muscle, whatever. The muscles have to, you cannot think. You cannot expect your brain to tell you which fingers to push. You have to do it automatically. 1 hour minimum every day to learn it. That's how the brain works. I mean, the brain works like that. Is it bad? Is it good? I'm not sure. This is what it is, though. All right? A little bit every day is going to take you long ways. Remember that. And you may kill yourself because there are people. I was doing that, the old thing. You know what I was doing when I was a student? Well, it was a different system and it was a different time. There were times that I would not study anything. And I was expecting the midterm and I would not sleep for 2 days. Guess what? Did not do anything. Doesn't matter if you don't sleep for 2 days to go and take the midterm if you have not spent the last 2 months, studying. So that's what I'm saying. It does not matter how many hours you spend. No, the brain does not work like this. You may spend 80 hours studying altogether, and somebody may spend 60 hours spread over time, and this person is going to do better. Okay, so be smart. Know how the brain works to be able, it's like you drive a car. If you drive a car, you have to know what the car can do. You cannot drive a car like a Corvette if it's a Chevy. I mean, you're going to destroy it. You cannot drive a Corvette like a Chevy either. You have to know how the brain works. All right, now we know so much more about the brain, then we can be smart on how we do things. In any case, this is what it is. Take your time to do that. Tell me if you have any problems or any experiences. This is an opportunity also for me to make some corrections. The other thing I wanted to say that you're going to see that I have decided out of practice and experience that the homework that is going to do on Sunday, but by 12 midnight, all right? 12 midnight, the homework is going to do. But still, the new homework is going to be available at 6, but you 12 midnight. And the other thing that the other class asked me to do, and I thought it made sense, because usually most of the students work on Sunday to solve the problems. And I don't blame anybody, that's what it is. There are so many classes, so many courses. I will have my Friday office hours on Sunday from 1 to 3. Okay? Sunday from 1 to 3. So I know you're going to be starting solving your problems, or you're going to be in the middle of this, and then I need to be available. All right? Instead of Friday. But Monday and Wednesday, and I have already made those changes. Monday and Wednesday will be right after the class, but Friday is going to be, instead of Friday after the class, it's going to be Sunday from 1 to 3. Okay? Any other comments, questions, suggestions? Yes.
So what's the timeline for teams being formed and when we can reach out to them?
Yes. So I have already received a couple of recommendations from students, recommendations of what they wish I could do for them in terms of placing them in teams. But we cannot really finalize anything because there is a week and a half for dropping the class, isn't it? And also change from one section to another. People do those things. And so we're not going to finalize. I'm not going to give you, I will give you something light in the beginning so we don't miss a week. But usually the work in the teams is going to happen after everything is final, because it's going to be bad if I give you something and then I change the team. And I have done that and I've learned what not to do. So, any other questions? Okay, I think we are good, right? 2 minutes before, but that's what we have for the class. This week was light, but it's good to be light and get to be introduced, all right, to the work. So Monday we'll
Wait.
start. Yes.
Excuse me, ma'am, is this top hat the homework for this weekend, this top hat quiz?
Yes,
Okay, thank you.
you're welcome. Okay, thank you so much. And I will see you on Monday, office hours on Sunday.
Another question.
Yes.
So I saw that the recordings for the last lecture wasn't uploaded.
Yeah, so here is what happens. The recording for the morning session is okay, but the afternoon session had some problems. So now I'm gonna check this recording. We made some changes in the setup. You know, when I heard the recording from here, it was like something was going wrong. So, but also the recordings will be on media side. So you're gonna try, I will put the recording for the morning section, and then we'll see what I'm gonna do. I have an iMovie. I may be able to go and fix some things, because what happened is it was going and then it would go back again and repeat for some reason. I don't know why. So I will, if I am able to fix it, I will upload it over the weekend.
Okay.
But I hope that today's recording is good. Thank you. Thank you.